Okay, so and so so now we've brought in these include the five functions, the azimuthal functions. So you can see that by and large everything is sort of symmetric around phi, and so you can look at these, and these are kind of instructive, but uh, um, they're they kind of give you an impression for the overall shape of orbitals, in the sense that they tell you where, if you look out in these different directions, now kind of as a sort of a 3D landscape in phi and in theta, um, where the probability density is going to be appreciable. Okay, and we see again that for any ML equals any ML state which is non-zero, if we look directly up, we see that there's zero probability density. That corresponds to, along the up or down, corresponds to the z-axis. Okay, so now let's talk about angular momentum. We've already seen that the quantum number ML quantizes the z component of the angular momentum. Okay, so L sub z, z component of the angular momentum, is m sub L times h bar, where again m sub L can run from 0 up to between minus L and plus L in integer steps. And it can also be shown, again, this is something which can be shown and is typically included in a quantum mechanics text, a more advanced quantum mechanics textbook, that the quantum number L specifies the magnitude of the total angular momentum, in that the magnitude of the total angular momentum L is equal to the square root of little l times little l plus 1 times h bar. Okay, and so for this reason, L is known as the orbital quantum number because it specifies the orbital angular momentum. Okay, the absolute value, the magnitude of the total of the orbital angular momentum. And I should say here that that m sub L is the magnetic quantum number, known as the magnetic quantum number, for reasons which you'll find out later on in your quantum mechanics studies. Basically, to have to do with the fact that if you apply a magnetic field, then the ML determines how these energy states. So the ML states are in general degenerate in energy, but when you apply magnetic field, the degeneracy is broken according to these values, the value of ML. Okay, so so we're not going to get into that, but that's it can be shown, and so of course, since L sub z is the projection of the total angular momentum onto the z-axis, and L is the total angular momentum, then we expect some relationship between L and LZ. And again, LZ is equal to MLH bar. L is equal to square root of L times L plus 1 H bar. And so what we see is that even though LZ is a component of L, LZ can never be equal to L. So the Z component of the angular momentum can never be equal to the total angular momentum, unless of course L is equal to 0. Okay, unless the trivial case where there's no somehow there's no orbital angular momentum. But except for the s orbitals, okay, then LZ can never be equal to L. Okay, so for example, if L equals 1 here, then square root of L times L plus 1 is just 2. And so we would have that L, the magnitude of the angular momentum, orbital angular momentum, would be root 2 times h bar. But the maximum value for the z component of the angular momentum is only 1 h bar. And so we see that that the maximum value of the projection, or the component LZ, is smaller than the total angular momentum. And this is interesting. So unless there is no angular momentum at all, any one component, for example the z component of the angular momentum, cannot account for all the angular momentum. So that is classically that can't be explained. You would expect that the angular momentum has a well-defined axis,